Hello, and welcome to my talk on shape data with Acsets. This is Acsets are a data structure that has come out of the AlgebraicJulia ecosystem. And what's AlgebraicJulia? AlgebraicJulia is a committee or a community of people who are interested in applying applied category theory to Julia and writing tools for applied category theory with Julia and writing tools for the sciences using applied category theory with Julia. And we have found Acsets, which are the data structure that we're going to talk about in this talk, very useful. So we're going to share it with you. The outline of this talk is that first we're going to actually tell you what an Acset is. We're going to do this by sort of building up an example. Then we'll give a formal definition. And finally, we'll try and impress you by showing you sort of a menagerie of things that are a small selection of a much larger menagerie of things that are captured by Acsets. Then we're going to talk a little bit about the implementation. And finally, we're going to talk about the bright future, the possibilities for what will happen with Acsets going on in the future. So what are Acsets? If I had to give sort of platitudes and a general idea of Acsets, well, I would say that they're a family of data structures. So I called them a data structure before. Really, they're a bunch of data structures parameterized by a schema, which I'll talk about later. And they're general. They show up everywhere. They're efficient. You can work with them. You can compute with them very fast. And they're useful. We use them everywhere. We couldn't live without them. So yeah, that's why we're so excited about them. The name Acset comes from attributed C set, and it's really not worth going into what that means. Just think of it as a new name. If I had to give a more concrete description without actually giving the definition, I would say that Acsets are sort of databases as values, and that's sort of the metaphor that I'm going to be working with for the rest of this talk. And we have a paper on this, which we have submitted to Compositionality, which is an applied category theory journal. And I will, at the end of the talk, I'll give more information on that if you want to learn more about Acsets after this talk. So without further, okay. Disclaimer. I've said AlgebraicJulia, we're interested in category theory. Acsets come out of category theory. However, you don't need to know category theory to use Acsets. So if you don't know any category theory, don't be afraid. And if you do know category theory, maybe you can see the influences, but you don't need it. It's there when you want it, but you don't need it. Okay. In order to get into the ideas behind Acsets, I'm going to rethink what a graph is and show you a different way of representing graphs than you might have seen before. That will sort of get you into the Acset spirit. So to represent a graph by a relational database, what you do is you have two tables. One is a table of edges, and one is a table of vertices. And in the table of edges, you have two columns, which give the source and target of each edge. Each edge is a row in the database. So for instance, in the first row here in the edge table has source 1 and target 2 and ID 1. So edge 1 goes from vertex 1 to vertex 2. Once you've represented a graph in this way, it becomes natural to add other attributes to the picture. So, for instance, you can add whether or not the edge is dotted, and you could add the shape of the vertex. You could imagine maybe having also more scientific columns. And this generalizes weighted graphs and property graphs. So now we're going to talk about exactly what an Acset is and give a more formal definition. So Accets are parameterized by schemas. So before we talk about exactly what an Acset is, we have to talk about what the schema for an Acset is. A schema is given by objects, which are the E and V here, mappings between objects, which are source and target, attribute types, which are dot type and shape, and then finally attributes, which are dots and shapes. And the idea here is that if you have an edge, then you can follow these arrows to get different things from that edge. So for instance, to get the source of an edge, you follow this arrow from edges to vertices, you follow source, and you get a vertex. In order to get the dots from an edge, you follow this arrow, and you get something dot type. In the database land, each of these arrows corresponds to a column from its source. So the table for edges has a dots column, a target column, and a source column. The table for vertices has a shape column, as you saw before. Now that once you've written down an Acset schema, you can talk about Accets on that schema. And this consists of, for every object in the schema, the set of primary keys. For every mapping, a function between primary keys. So, for instance, it sends a primary key for an edge to a primary key for a vertex. For each attribute type, a concrete type. So attribute types are generic, but to actually have an attribute, you have to choose a concrete type. And then for every attribute, a function from the primary keys to that concrete type. So this will make a little bit more sense when we look at our previous example in this framework. So the set of primary keys for edges is 1, 2, 3, 4, 5. Set of primary keys for vertices is 1, 2, 3, 4. F of source is a function which takes primary keys for edges to primary keys for vertices. And if we apply it like element-wise to this list, we get the column. So when applied to the primary key 1, we get the primary key 1. When applied to the primary key 4, we get the primary key 3, as you can see in this column. We choose concrete types for each attribute type. So dot type is bool, and shape is symbol. And then we give the columns for the attributes like this. So hopefully you should think about this a little bit and see how this more formal definition maps to the more informal definition in terms of tables. Okay, and now we're going to do a speed run of a couple interesting other data structures that you can do with Accets. So first up, Petri nets. A Petri net you can also think of as a bipartite graph. And it's used by chemists to represent chemical reactions. Species are what chemists call molecules or like proteins or whatever. And then transitions are reactions. So each transition you can see are the red boxes, and they have input species and output species, which are given by the arrows. And in AlgebraicJulia, we use this data structure to simulate chemical reactions. And it's useful. Another type of Acset that you can use is typed circular port graphs. So there's like a whole menagerie of different variants on port graphs based on, okay, well, the ports and the wires can have types or not have types. You can have you can have two different types of ports. You can have input ports and output ports. You can have outer ports, which are a different thing. And all of them have different schemas. Here is one particular type of port graph, which is a typed circular port graph. So there's only one type of port. Each port, to each port is assigned a box. To each wire is assigned a source and target port. And then finally, wires and ports both have types. And the final element of our menagerie is an undirected wiring diagram, which sort of represents a pattern for composing, say, electronic circuits. So you can imagine in each of these holes, you could put an electronic circuit, and then it would be connected to sort of external electronic circuits through these outside ports, and then other electronic circuits within the big circle through these wires. And unlike before, the wires don't have sources and targets. The wires are just sort of, well, just like a breadboard. If you've seen a breadboard, you just sort of attach everything to a common a thread, which is the junction. So each port is attached to a junction, and everything that's attached to a junction sort of communicates to each other. And now you can actually look at the schema and see how it maps to this diagram. You have the inner circles are the boxes. Then there are ports, which are attached to boxes. Then there are outer ports, which we visualize as being on the big circle. And then both outer ports and ports are attached to junctions, which are the little circles. And then finally, outer ports, junctions, and ports all have types. So this is, we do all sorts of things with undirected wiring diagrams. We do queries with them. We compose dynamical systems with them. They're very useful. And they're, like before, there are lots of variants. I've only shown you one variant. Okay, so that sort of finishes the more mathy side, and now we're going to talk about how we implement these and how they go fast. So one of the cool things about Acsets is that not only are they general, but they're actually efficient, and we'll give benchmarks at the end too. And to give an idea of what our implementation looks like, I'm just going to give a demo. So first step, of course, in any Julia project, you got to import. So we're using Catlab. Everything in AlgebraicJulia uses Catlab. The next step is to write down a schema. So this is actually, the @present macro is sort of a generic Catlab macro that does a lot of things, but here we're using it to write down a schema. Don't worry exactly about the details, but you should recognize the shape. So we have objects, mappings. In category theory term, they're called homomorphisms. So that's where hom comes from. Don't worry about that. Then we have the attribute types, dot type and shape, and finally the attributes. Now that we've written down the schema, we can declare the type. The type takes in this sort of a type constructor that wraps around a lot of type parameter magic. And it takes in an index parameter, which we will talk about a little bit later, but basically it caches the inverse map to source. And now we can actually write down an Acset using another handy dandy macro. And this Acset will be the Acset that you should be familiar with by now, because we've seen it a lot. So 5 edges, 4 vertices, familiar source map, familiar target map, and then dots and shapes. And then after we've written this down, we're going to mutate it a little bit. But first, you get to see that there's some nice pretty printing. So it's going to print out in tables. Check it out. Now we're going to add an edge. So parts, yeah, we're going to add a part, type edge with source 4, target 1, and it's going to have dots. And now if we print out the Acset again, you'll see that the edge is added. It's edge 6. And now we're going to, you can, not only can you get the source and target from an edge, you can also get what edges have like vertex 4 as their target. Now we're actually going to do a little bit of category theory. We're going to take this graph and juxtapose it with itself, which is in category theory, this is known as a coproduct. And yeah, so you called coproduct, F and F. You could juxtapose two graphs by themselves. And now this is going to print out a big old table with 12 edges and 8 vertices. But yeah, once these are big, it's hard to visualize. So now we're going to write a little function that will actually draw our Acset, and this will give you a little bit of an idea of how the API works. So we take in a decorated graph, and then we're going to build a property graph out of it, which is a graph where each vertex and edge has arbitrary properties, and this is used to convert to graph viz. And now you see that we can iterate through all of the vertices by saying for v in parts g v. And then we're going to set the shape. We're going to, we added all the vertices of v to pg, and now we're setting properties on them. So we're setting the shape. Oh, well, I fixed that at the end. I pre-recorded this, but yeah, you can see the shape parameters twice. Anyways, now we're adding edges to the property graph, and subpart gives the vector of source and the vector of target. And now for each edge, we're setting its attributes. We're setting properties, so we're setting the label, and we're setting the style. Yeah, you're going to see later on it's going to give an error for these two, and I'm going to correct them both. And just sort of let this all wash over you. Don't worry about understanding this exactly, but this is just sort of how this looks like in a broader context. The low-level interface to this all is actually pretty imperative. So it's not like fancy functional programming, category theory. It's all just like it's pretty low level. It's just mutating databases, adding parts, setting stuff, iterating with for loops. Yeah, you see. Now I'm fixing it. So okay, I fixed the shape, and now I fixed the style. So now it's actually dotted. Yeah. Okay. Now that you've seen Acets in practice, we're gonna dive in a little bit into the internals. So when we constructed that Acset type, it looks something like this. So we store the number of vertices, the number of edges, and then we store the shape for each vertex, a source for each edge, target for each edge, dot type for each edge, and then we have the indexes which the source index for each vertex, there's a vector of all of the edges that have that vertex as a source. And in graph algorithms, this allows you to compute the neighbors of a vertex very quickly. And having the forward map and the backwards map is very convenient. However, keeping them in sync is quite tricky. And if you were to manually implement this, you could mess up, and it's just very fiddly. So one of the advantages of Acsets is that we actually generate all of this code for you, and that means that it's fast and correct. And this is sort of an example of what this looks like. We have an @generated function, which I don't know. This is JuliaCon, so maybe you've heard of generated functions, but they're not the most common feature of Julia. But basically, they're like macros, except instead of taking in syntax, you take in types. And because Acsets are parameterized by their schemas, then you can actually generate code for all of the mutators and accessors, and that code is fast and correct. And what this enables us to do is this actually enables us to compete with specialized implementation. So LightGraphs is a quite fast graph library that's handwritten. And despite having no specific code for in the core Acset implementation, we can sort of build graphs on top of it and compete with LightGraphs while still being fully generic. So not only is this useful in general, but it's actually good for high performance computing. And now finally, I'm going to talk a little bit about what's in the future. So these are just some ideas that we've had to extend Acsets, and hopefully this will show you that the basic idea is extensible and interesting. So one idea is to have matrix valued columns. So instead of one-dimensional columns, have two-dimensional columns. Another idea is to make Acsets parallel or distributed, and then algorithms that we write we can write algorithms, generic parallel algorithms, which are tricky. We can write them generically over all Acsets, and maybe even code for that to make it go really fast. And then a third extension is Acsets where the morphisms are mapped to things other than just functions. So relations or linear maps, or non-deterministic functions. And then another exciting thing in the future of Acsets is semagrams, which is best explained with a demo. Essentially, semagrams allow you in a Jupyter notebook to edit Acsets with in a very generic way. It works for lots of different types of Acsets. And inline in the Jupyter notebook, you can edit them with your mouse and your keyboard in a very graphical, intuitive manner. So you can see you add vertices, make wires between them. You can edit the attributes. And this is all generic. There's no special purpose code for like decorated graphs, but because semagrams is general enough, it works. And now we've come to the end of the talk. I hope that I've convinced you that Acsets are general, useful, and efficient. And I hope that this is the end of the talk, but the beginning of more people in Julia trying out Acsets. And I will be, as I'm recording this, but I will be there for any questions. So thank you.